So in our previous video, I was just giving you an introduction about how stars form, the initial stages of star formation, where you have a molecular gas which starts cooling down, and as it cools down, it starts to collapse, and as it collapses, we end up forming a star, right? Now let's go a little bit more into like detail behind the story behind this collapse. I gave you a brief introduction on how this collapse starts, right? So you imagine I have a cloud of gas with me. Now this cloud of gas has some pockets of metals, or again I have to reiterate, metals means anything that is heavier than helium is a metal for us. So even carbon, whatever, right? So there are like small pockets, like imagine there's like a gas in front of me, there are like some small pockets in between, right? Now these small pockets will start to cool down the material around it by absorbing, like say, energy, by absorbing photons, moving its electron to a high energy, and then like to an excited state and back to ground state. All these drama will happen, and it will start to cool down the material around it, the gas around it. Now as the gas starts cooling down, right, if I have to go back to thermodynamics, as the temperature goes down, the volume also starts coming down. Now as the volume starts coming down, the gas will start to collapse inwards. Now it's given now the point is, there is like at one point I've collapsed, I've packed enough material, okay, in a small area because of all these small impurities in between. They have cooled down the material enough, and they've brought enough atoms and molecules together into a gas into a small pocket, which now is going to increase the mass over there. So that means I have a small mass concentration. Now what happens because of the mass concentration? Well, our good old friend Newton steps in, or Einstein. So where acid collapses and falls, comes together, gravity takes over. Now gravity, once it steps in, it's going to start winning the game. At these macro levels, there is like this famous equation, this is in theoretical physics. At these macro levels, gravity plays a significant role. In the microcosm, right, at the level of atoms and fundamental particles, gravity actually loses the game as compared to the other forces, the fundamental forces. So in this state, gravity actually is the dominant fellow over here. He's the big guy. So gravity is now you've given the initial conditions for gravity, right? Now you can sit back and let gravity take care of the rest of the work for you. Now gravity is now going to start pulling all the material towards its center, because you've built enough gravitational potential over there. Now as it comes, pushes in, now in the previous video I again said, right, like now gravity is pushing all the material in, and the gas together. Now that means it is building up pressure, because at some point, okay, there is cooling and the volume comes down, and there is a point of thermal equilibrium where it is now, okay, boss, I'm stable now. No, at that point there is this third guy into the picture where gravity steps in and say, oh wait, you've packed up enough material, you have enough density over here for me to start playing. So gravity now starts pulling everything together. Now as gravity pulls in the material together, as gravity starts pulling the material in together, it basically starts to increase the pressure in this area, right? I'm going to push the material even further in, because I'm gravity. I want to pull all my things back to the center. That's my job as gravity, right? So that's the whole point. I'm trying to pull everything back down to the center. So which means I'm going to build up pressure here. As I build up pressure, the temperature goes up. As the temperature goes up, now, well, the volume tries to come out again, right? Now the gas, there's like now an outward pressure. Gravity is trying to give an inward pressure, and because now the gas is heating up, it tries to push it back out. And now it's almost like, like there is a sack of rice. You're trying to push the sack of rice. You can push it a little bit, right? You can push the sack of the rice in that sack by a little bit, but after some point you'll start feeling a pressure coming back out. Imagine every single rice grain as a as a gas molecule over there, or a gas atom over there. It's going to push it back. Okay, in the case of rice, it wasn't temperature, it's just because of its volume. But in this case, the gas, as it comes closer and closer, the pressure goes up. As the pressure goes up, the temperature goes up. As the temperature comes up, it tries to give an opposite pressure back out. So now there is now a battle between gravity and the thermal pressure, right? Now gravity and the thermal force are now fighting against each other. One is trying to push everything in, the other is trying to push everything out. Now at this point, you have built enough potential energy, which is our gravitational potential energy, and also there will be a second potential energy which is formed inside due to the temperature. Okay, so I'll just give, like, I'm not going to put in much of constants and all the numbers over here. I'm just going to give a rough equation. Now gravitational potential is Gm over R. Now I've put everything in this. All the gas molecules are here. That's my radius R. And all these things have a gas mass of m, right? I have to pull everything inwards. This is what gravity is trying to do, push everything inwards. But then these gas molecules are now going to push this thing back outwards because of temperature, which again I can write it as the Boltzmann constant times the temperature. So this is, I mean, it's not exact equal, but it's rough equality. There's some 3 over 5 over here, and yeah, so on. So the whole point is there is a gravitational potential, and also there's like some thermal energy inside, right? Now gravity still wins the game. It still continues pushing things inwards, and at one stage these two will be equal, and when they are exactly equal is what we call as the moment of hydrostatic equilibrium. Okay, we call it hydrostatic or thermal equilibrium. We reach a state of equilibrium. At this point, if I have enough material over here, that means my gravitational potential would be sufficient enough to increase my temperature to a really good level. I have enough material to push my gravitational potential up. My temperature is going to be high enough, and the pressure is also high enough, so that now my two hydrogen atoms over here, there are two guys over here, they're going to fuse and end up forming helium. When they start fusing and forming helium, well, I can officially now say that's a star, because the purpose of the star has now started, right? The whole duty of a star has now started. Now this is what I might have mentioned a word in the past, which is called the virialization. Okay, what I mean by virialization is similar to the work energy theorem, where my kinetic energy, which I'll mention as K, kinetic energy is 1/2 of my potential energy. Right? So now I know my potential energy. Now my kinetic energy is going to be half mv square equals my potential energy, right? Which is kb over t. Over t, kb times t, and this is going to be half of my potential energy. So through this, there will be some prefactors. So let me ignore all these half and whatnot. Through this equality, right, now I can calculate the mass of my star, because I know what is the temperature of the final temperature of the gas, and through spectroscopy I'll know like what is the velocity of all these materials over there. So I will know what is the mass of my star. I can calculate the mass of my star. So now based on the initial conditions, right, the mass of the star is defined. Now this again, I have to go back to our fundamental constants. All these fundamental Boltzmann constant and everything plays a key role over here. If something is off, our sun won't be of the same mass. If our sun is not of the same mass, our earth, like it will be more hotter, it's going to be in a different state, and well, maybe our earth will be in a different, at a different radius and not where we are right now. And who knows, you know, the elements and everything. So that will be another video which I'll do at a later point in time. That the earth will have different composition because of the situation over there, which I will come to later. But now you understood like how a star forms. Basically the gravitational potential is pulling material in, it heats up the material tries to push it back out. You now have a huge potential energy that is formed in, and if the mass is high enough, it basically ends up forming a star. Now you might have a question to me after this. So Balaji, what happens if the mass is not high enough? I mean, the work has started. I've pushed the cooling has happened, material has compressed, but I don't have enough material. Like I don't have enough mass to start with. I haven't compressed it enough. So my gravitational potential is not high enough to push my temperature high enough to start the nuclear fusion process, right? So my virialization didn't happen. What happens at this stage? Are there any such failed stars? Well, the answer is yes. There are failed stars, what we call as brown dwarfs. So brown dwarfs they have a similar formation process as how a star forms. But because they don't have enough material, they can't virialize because the temperature is not high enough to fuse two hydrogen atoms into helium. So it can't achieve that equilibrium and virialization. The mass is not high enough. Now, what is that limit? How much mass should I need to have in my initial condition to actually like have a star at the end, right? Actually, this one, like everyone would have heard about the famous Chandrasekhar limit, which says like if a star is about 1.2 times the less than 1.2 times the mass of sun, it ends up being a white dwarf. But I'll come to that later on in another video. But right now, there's a famous astrophysicist, Subramanian Chandrasekhar, who is a Nobel laureate. He won Nobel Prize for this, right? He's the nephew of Sir C.V. Raman. We all know about Chandrasekhar, we all know about Raman. There's another Indian astronomer that we don't know about. His name is actually Kumar. There is a famous Kumar limit, which is if the mass of the star is less than 0.08 times the solar mass. Typically, if you look into astrophysics papers, like mass of the sun is represented as m with a 0 and a dot in between. So that's what we call as a solar mass. So if the mass of a star is less than or equal to 0.08 times the mass of sun, it won't have enough. So anything less than 0.08 times the mass of sun is not enough to actually virialize. So we can't virialize and it ends up being a brown dwarf. So this is what we call as the Kumar's limit. Like with this, we will know who. There are these. You can search. There are no actual images of brown dwarfs. There are like some fuzzy images of brown dwarfs. There are some artist rendition of brown dwarf, which I can probably put it here. But yeah, these are what we call as the failed stars. Now this is one part of the storyline. Now, how big of a star can we form? Right? Now, okay, I told you about the lower limit in this entire game. What is the upper limit in this game? The upper limit is actually high enough. So the whole point is how much material can I cool and bring down, right? Now that means the more bring them close together, cool and compress together. How much material can I do it? Now that efficiency depends on the cooling process. Now not everything can cool that efficiently, right? So it depends on the cooling process and also like the initial conditions. So typically there are different, now metals can cool in different way, like carbon and all these materials, they can cool the gas in a different way, so then they can pull it back in. Now, okay, now let's roll back. Now this happened 4.5 billion years ago, forming, well, our star, the sun. Now let's roll the time back some more time. Let's go to this where we left off in our initial videos, which is the Big Bang, right? After the Big Bang, now we are sitting in a soup of mainly hydrogen and a little bit of helium. That's it. Helium is not that efficient in cooling. I need super heavy elements like carbon and so on, to silicon and so on, to actually start cooling efficiently to start this process. So how did the initial stars form? Because how did we end up with this carbon? I mean, I didn't buy it from, the universe didn't go to a shop and bought some carbon. Where did it get this carbon from? The carbon was actually processed inside a star. So now we are in a chicken and egg problem. Which came first? The star, right? Like the molecular gas or the star, right? Now I need carbon to form a star, but to have the carbon, I need a star. So then how did I get the carbon in the first place? Or I'm just giving carbon as an example. There are a lot of other metals which can do it, but now I only have hydrogen and helium at hand. To cool, I need something else to cool efficiently, like carbon and so on, to form like solar mass or similar stars like what we see around us, right? Now back then we were in a super metal poor environment. So what is happening then? Then how did we form, like, so what was that initial star that formed carbon? This is what we call as like the population 3 stars. The whole point with population 3 stars is we haven't seen a population 3 star yet. It's still on paper. We can see the effects of population 3 stars, okay? Like say epoch of reionization and so on. We can see the effects of population 3 stars in like say few of our other data, but we haven't actually seen a star that is population 3 star. Now the whole point of population 3 star is these stars formed in the early universe where there was absolutely no metal. So how did the cooling happen? Because without cooling I can't form a star, right? How did that initial cooling happen? Fortunately at that point we had some hydrogen molecules, right? H2. Now H2 can do a little bit of cooling actually. H2 molecules, because of their rotational and vibrational properties, they can actually start cooling down, okay? Now because of this cooling effect, now I can actually compress enough material to virialize and to form a star. Now typically these star masses are about few hundreds to a few thousand solar masses. So they are about like few hundreds solar mass to few thousands of solar mass. So I can't like pinpoint like a right amount, but yeah, they are like super massive stars. Okay, they are ginormous stars, but we haven't seen those stars. They're really big, but we haven't seen it because these stars could have possibly existed, you know, in like because it was during like the age where we were only primarily having hydrogen and molecular hydrogen. And if you watch my previous videos, I would have called this time as the dark ages of the universe, because at this time there was no reionization, so there was no point for a photon to be emitted, right? So this hydrogen gas, like the molecular hydrogen, what we suspect as POP3 stars is would have cooled down that initial soup of hydrogen, like initial soup of gas. It would have brought it down, virialized a little bit, and it would have started this POP3 stars. The second point over here is, this is another interesting aspect about the POP3 stars is, the heavier the star is, right, the more gravitational potential it has. That means the pressure is going to be even more higher, which means it will burn the fuel faster. That is, the nuclear fusion will be done faster. So as the nuclear fusion is done faster, they're going to be super short-lived stars, and they will explode in a supernova as soon as that process is done. So that means these are all like ultra short-lived stars. Our sun has survived for 4.5 billion years till now, and it still has another 4.5 billion years from now on. 9 billion years. This is like super long life for a star, for a POP3 star. For a POP3 star, they don't last that long because they are super massive, which means the pressure is super heavy. They're going to burn everything efficiently, and like now this is where it is going to start seeding more heavier elements for us that will then slowly start forming all the metals and everything that we see around, like the carbon that is made in your body, right, was once synthesized inside a star. The universe never had carbon to start with. The carbon, the nitrogen, the oxygen, the iron, everything that you see around you, like the things that makes you right now, it was all synthesized inside a star or around a star, like heavier elements. We can't synthesize super heavy elements like uranium, plutonium inside a star, but that happens because of some other processes that happens around a star, which is like typically by a proton capture or a neutron capture. So there are like few nuclear synthesis processes that can happen. I'll explain it later. There is R process, S process, and P process, rapid proton capture process. That's how these heavier elements are formed. But I just wanted to leave you with what are POP3 stars, how they form, and these POP3 stars are what we assume to be the initial stars to solve the chicken and egg problem. Because to cool, I need heavier material. To have those heavier material, I need a star. So that means a star should have formed at some point. Now our guess is POP3 stars, which should have formed through H2 cooling. And with this I'll stop it with I'll stop for this video, and in the next video I will go further down into planet formation, which I'll like probably give you a brief introduction about it right now in the last 5 minutes of this video. So now we have the star formed, right? Now did all the material that collapsed ended up forming a star? The answer is no. Now what happens is, as I collapse, I can't just collapse material like this. Now what happens is there is some velocity associated with it, right? Like gas molecules are going to go randomly around. Now I need to, there is like still, I need to conserve, I still have to obey the laws of physics. I can't just go off, right? I mean, I've conserved the laws of, energy conservation. That's how I realized. Law of energy conservation, I've saved it up. But there is some kinetics involved in here. That means I need to also conserve angular momentum, right? There is a conservation of angular momentum. So what happens is, not all the material ended up in the star. There will be some leftover material that was just, leftover material that just stands around. So typically this is about, 1% to 10% of the star mass. Okay, the star's mass will be left out. The rest would have been in the star. So what happens is, this star would have started spinning to conserve angular momentum while it is collapsing. So it would have started to have a rotational motion. Our sun has a rotational motion. The sun goes around itself once every, I think, 24 days. Now what happens is, now the star would have started rotating, and it would have started having it would have started shining, right? Now we have the star. Voila, everything now shines and beautiful. Our sun is there. But there are still some leftover material, and because of this conservation of angular momentum, the leftover material actually will start collapsing itself into a disk around the star. This is more like a side view. If I do a top view, you will see something like a star over here at the center, and then like there might be a little bit of a gap, and you'll see all the material around it. Actually, I'll post up some videos. There is like one famous star which is where you can see the protoplanetary disk, which is HL tau. So there's an image of a submillimeter image where you can see this material. So this is from where we end up forming planets, and I'll cover it up in a later series. In the next series, I'll cover up how a planet forms. So I just want to leave you with this. So there are images of protoplanetary disks that we have recently acquired. So there are some really good images of protoplanetary disks and planet formation. I'll start showing and explaining to you how, now that I have formed a star, how did planets form around it. So with that, I'll leave you. Please subscribe to our channel and like our videos and follow us for more content.